So and check if my pointer works too. Perfect. So this is such a better room compared to the other room. And welcome to class 6316. So just to again clarify, if you already took my undergrad version of the course, you don't need to take this class because the homeworks will be a lot similar, but we have more advanced programming question there, but just a little bit advanced. And also quizzes. It's just the old midterm and final, I just decompose it into 12 quizzes. And you can be absent for up to 2 quizzes. Only the top 10 quizzes will be counted into your degree. So that's so much, give you a little bit of flexibility. You know, maybe you have to be absent for a few cases. So everyone needs to have 10 quizzes to be counted. You can take all the 12 and take the top 10. And that's about quizzes. So I already posted the dates of the quizzes in the schedule page. So feel free to check it out. And assignment of the homework 1 will be posted by tonight. So most assignments will be due in 2 weeks. And so there's a NumPy tutorial I posted for like a reading material as the last column in the schedule page. Please, please read it if you're not as fluent as you want for using Python or NumPy. Okay, so let's get started. So honestly, I normally treat my first class more like just preparation, logistics, all this other issues, or and plus the minimal test. So this is the true first class. And because we got a better room, so I just make the classroom class size larger into 1 to 105. And I think almost everyone wants to take this, already being part of the class already. So if you're still the wait list, then email me, and I can just include you in the roster. So everything will be announced through the email list. So you should already receive the emails from me about the room change and about the lecture website. So that's it. So I covered a little bit last about the first lecture, the first 2. I just want to go over really quickly again. So lecture again, so the location of our website, so that website URL, and also we want to focus on more mathematical derivation, and we focus on developing skills rather than feeding you the knowledge itself. And so, so background, you already know by that quiz 0, and the basics is like all the background there and why we're doing so. And so I always like to show this page because I think machine learning in the end is really just a module. So there's a lot of similar terms, right? Data, like data science, machine learning, so statistics, AI. So how do you think about the positions in the bigger pictures? And I think this is a good summary of the bigger pictures. So in terms of data science, there's so much functions involved, right? You have to capture, storage, efficient management, and machine learning is just part of it. It's a good tool to mine the patterns, but all the other parts are important parts. They are, if without good data capturing of data, the visualization, you can't push to the customers, you can't get enough data from the customers, from whoever that data matters to them, and all the other parts are important. If you think about it, this whole pipeline builds an ecosystem, right? So the reason why machine learning dominating, and maybe a little bit more dominating than statistics, and we are using a lot of statistics, the method, the theorems, as part, and the thing is, computer science itself building an ecosystem, right? We're building from start to the end. And that's why it's so powerful. It's not just about a module, it's a whole pipeline, it's a whole end-to-end toolbox. So keep this in mind. And also machine learning itself is not just statistical modeling. And there's a lot to consider if you think from the perspective we are part of this ecosystem, right? How do you make the most efficient data retrieval by making use of the library behind? How do you make use of the good security mechanism developed in crypto and make more private machine learning or secure machine learning? And all those can be part of the consideration and make your model, make your current method very much more advanced than just the statistical modeling itself. So that's why I feel this view about what's the bigger picture, it's really very, very important. And then all the other, we talk about basics. So we're trying to build a program. And no matter what, this is a computer program. And just a slightly different here is the traditional programming is having the data and the programmer using the rules or whatever and feeding to the computer and generate output. Very different in the machine learning case, the training phase, is you're feeding the data and output Y, and through the computer, you're generating a function f. So you're using the label data to generate a program. So this part is fundamentally different from the traditional programming. But in the end, it's still a program. It's still a computer program. The properties and the needs, it should be similar to all the software engineering classes you already learned. So what should be a good computer program? You all learned it from hopefully your software engineering class, programming basic class, right? So keep this in mind too. And that's also very, very important to realize what's the differences, but what's the similarities compared to the traditional computer programs. Questions? Question here? Okay. So we covered. So what do you know? What do you even mean to generate a program, right? So this x and y is your input, but you can actually just geometrically put the x properties as convert them into points in the input space. In this case, there are two dimensions, the x1, x2, and y is the labels or the shape in this case. So red square is class 1. I think class 1, yeah. Class -1, and red circle is class +1. And the program I'm learning is to classify the two, which is just a line in this case. And this gives you, okay, how should I represent the line? And you learned in your linear algebra class to figure out the line, you need a slope, you need the intercept. You just need to figure out that W and B, and then you know the good line to separate the two, the given x1 pair. So this we covered. Questions from last class. All right. So this is just a given x, y, right? But in fact, if you think about this is a program, right? What is the property of a program when you're doing programming and you want your program to work really well on a range of inputs, right? So in this case, not just precisely those given x and y pair, those given exactly those data, but some data very similar. So for example, this question mark, it's here. So how should I decide the class of that question pair? So I hope my line separate really well on the future data. The data not in my given reference x1 pair set, not in my training data. And if that's this data, I hope it's separate well into minus class, this into positive class, and I want that prediction to be as good as possible. So that process we just go virtually involves several important concepts of machine learning. The first is training. It's about figuring out the program. So in our case, because we know the program is a linear line, it's to figure out W and B. And that X and Y pair you feed into computer is called training set, a set of training points. And how do you look for the WB? You normally need to minimize some kind of error function, or we normally call that loss function. We're going to see details about what type of loss function fit for different situations. So this is how you figure out WB, by minimizing some error functions. And then the testing phase is, so I write out this program. I want the program to behave well. So how do I know it behaves well? So this is the phase from testing phase. So assuming you have a set of question mark data, you know their locations, their position is x1, x2, and you also know their labels. And then by using this program, you feed in this testing data into the program, you got fx question marks. Then you compare the true label, y question mark, versus this f question marks. This is how you know how it behaves. How it behaves. And the whole thing is about, I'm trying to get a program generalized well. And this is trying to get the generalization error. How it behaves, it kind of simulate and to get how this program that I just wrote behaves in the future data. So this is the testing phase. And the most important is because our aim of a machine learning training is to learn the functions of hypothesis of the programs from past data to explain, predict, model, or control the new data. And this is the most important goal. Question about this. Generalization. We're looking for to have a program can predict future points well, or control future points well, or model future points well. Sure.
Do we always need to have past data?
Good question. So in some setting, you actually don't. You collect the data when you go. Like reinforcement learning, you actually can you just go to whatever you behave. You got that data. You use this instant feedback to answer your current training data. But that's not. We're not going to cover that. Yeah. So we're going to cover basics for now. Okay. So and then that loss function is so. We have the blue point, square, red point, but we're looking for a line to separate the two classes, right? But in fact, there are many possible lines. You can put line like this, like that. There's just enormous possibility to put that line to separate the two classes that represented by the given training data. Where do you put it? So there are a lot of heuristics or theoretical, like guided strategy to figure out which line generalize well on the future data. So there's a little bit shift. I think there's version differences with my office and the office here. So I'm going to fix this in the slides posted online. So for example, this uses L2 regularization to figure out to use this line to separate the two classes, not using a line, but use a band. So make it as wide as possible. You can theoretically prove this generalized a lot better compared to just arbitrarily training get a line by just minimizing that loss. So regularization loss function, and then we put this as the last summary of last lecture. This the most important like a mental representation. Keep in mind about the whole class. So whenever you think about when you have this machine learning problem or data prediction problem, figuring out what is the task, and then figuring out what is the representation. If I'm doing classification, is it possible to use a linear separation hyperplane to separate my two classes or three classes or C classes? That's the representation, and scoring function is this area. How do you measure the predictions versus fx versus the y? And then after you figure out the error function, how do you optimize and to look for the best program that optimize that error function? And also, what is the parameter related to my program? So again, we aim to generalize well to unseen data. Here, unseen refers to the training set. So I haven't seen that data in the given X1 pair to my computer. That's used to train my program. Generalize well to the unseen data, future data. Remember this. This is the mental representation. We'll keep coming back, and we're going to use this to organize every lectures we're going to cover. Questions or something I haven't explained clearly, just feel free to chime in. All right. So then is the rough plan. Sorry. So this is again to tradition versus, yeah, it's all shifted. Okay, so traditionally you have data program go to output, in this case learning phase. In the learning phase of machine learning, you have X and Y pair, and you use computer to learn the program F, right? This is just the learning phase. So the learning phase can be also decomposed into multiple modules. You can think about more like a pseudo pipeline. You normally have the low-level sensing modules, which is just I said. I mean, there has to be a sensing data capturing module, and then after data capturing, you need to do data pre-processing. The pre-processing of data cleaning step, and after the data cleaning step, you need to figure out the right features like this X1, X2. I'm using those to representing my instances or my samples. What features to use? And then in a lot of cases, you have just too many features, more than enough, more than informative. How do you select good features? And that's the feature selection module. So sensing, think about capturing, pre-processing, feature extraction, feature selection, until here, you get X. And this is what we meant, and in the previous pages, those data examples are represented in an input space X. And here is that space. And you try to learn F function from X to Y. And then you use this F function to perform prediction, inference, or recognition. So, and you also have evaluation module. And from here to here, it's more of a training phase. But you also have the operational phase, right? So like I said, in the training phase, you have X, Y pair given to a computer. You learned F function out. You learned a computer program out. But when you use it, push it to deploy it to the true situation you want to use it, that's the operational or deployment phase, which is almost the same as the traditional computer program. You have the computer program, you have the data, and there's some kind of execution engines, and then you got the prediction output out. If you think about this deployment phase, it's almost the same as the traditional computer program. Input, program, feed into computer execute that program on the data, and you got the output. And the differences is how do you get that program? It's the training phase. So 2 phases, and we focus on training phase in this class. So because my CS computer science background, so I try to connect models to the computer program. This is maybe a little bit odd to students took Coursera classes before, because people normally just say model. But in computer science setting, we can think about that. Model is just a computer program. It has all the properties we aim for, and also we need to test. We need to software engineering, just like other computer programs. It's just the generation phase is different. The representation of the program is also different from other programs, right? Other programs have case control flow, for loop, branches, data flow, control flow. Here, the F function is mostly represented by mathematical functions. Right? So you can actually tell, there are a lot of variation in this pipeline, right? Because we are focusing on the training phase in this course. So there's so many variations. There may be different feature selection, different feature extraction, different representation of F, different representation of Y. That creates the variation of many different machine learning models. And what we covered last time also, I just covered the supervised binary classification is the most elementary machine learning formulation. And you actually can, so if assuming, somehow it's kind of shift. So we just mentioned in the program when you train, you want to have X and Y both feed into a computer to learn a program, right? But there are cases there's no Y. If there's no Y, and this is a classic, so if you have Y, that's called supervised learning. You can think about I'm using Y as supervision signals. That's called supervised learning. When you have no Y, you have no supervision. This is called unsupervised learning. And inside unsupervised learning, there are many different variations. So the most elementary unsupervised learning is something called clustering. So okay, I just put the points as I put the data as points in that X space, and using density, I just use density to cluster those densely connected points into a group. That's the simplest method we normally use. It's like a grouping, right? In the end, it's just a grouping. It's a strategy, you group points without guidance. There are also a lot of variation of unsupervised learning. So now, it's generative models. So without labels, I want to generate samples. So the most eye-catching, generative adversary network, again, it's also in this category. So the basic version, you have no label, just trying to get a program to generate samples look exactly or very similar to what I observed before. So that's the other type of unsupervised learning. Okay, no Y. So we have Y as the first variation, and the second variation, there's no Y. And there's also other cases, like in this case. So, for example, I'm trying to label each pixels in this image into different class. So this parts of pixels is sky. This parts of pixels are part of building, and this part is the car, and this part is the road. So in the end, my sample, the one I'm trying to classify here, is a pixel. I'm trying to label that pixel into one of the 4 classes, right? There are only 4 in this case. However, when doing this labeling, doing this classification, there's a very strong correlation, very strong singularity of my neighbors. If my neighbor is a sky pixel, highly likely, I'm also a sky pixel. So this is called structured classification, structured supervised learning. How do you use models to represent that singularity, spatial correlations among labels, among inputs? So this is called structured output prediction or structured input prediction. There's a structure among the samples. So this is not just for image labeling tab, it's also for NLP, the dog chased the cat. So if you want to have the part of speech text to be labeled for each of the word there, it has very strong grammar singularity, what you should predict. So how do you add those into the modeling? It's a very important big chunk of machine learning. So there's spatial, temporal, relational, there are many of those, and they all belongs to structured output learning. Questions here? Okay. Yeah, so there's also some people think this is more like a vintage type of research called a kernel machine. So it's actually the input is very complicated. I want to measure how do this similar compared to this versus this similar to this. So how do you represent the relationship of different very complicated input samples? So there's a very big group of method called the kernel method to design how do you capture the the relationships of similarity among graph, among sequences, among 3D structures, inside something called support vector machine framework. So in the end, you're trying to design method to measure the relationship among complicated inputs. And more recently, it's the dominating representation learning or feature learning from mostly from the deep learning field. They're trying to get to learn the features rather than extract features using domain experts prior. We're trying to design end-to-end pipeline to extract features automatically. So there's a lot of this layer-wise structure, embedding-based approach, or per layer-wide pre-training, or auto like VAE. There are many in this category. So we're going to cover CNN and RNN in one of the homeworks, but not too in-depth coverage of deep learning. So I think we have a course about deep learning for visual recognition. So that course will cover much more about deep learning approach and state-of-the-art advances. So the fundamental idea is just to convert from before the deep learning regime, people mostly spend time, the data scientists or machine learning scientists spend a lot of time doing feature engineering. And now there's this new idea I'm trying to adapt to have this transferable structure to be able to adapt to similar new tasks to learn the features automatically. So it's kind of dominating the industry, but there's also something, don't think this is more like a magic bullet. It will work on whatever problem you have. It still have a lot of limitations. and we're going to cover in the deep learning session. So again, so this is just to line this from we used to the beginning of AI, the beginning of machine learning. It starts from a rule-based system, just more all those knowledge-based traditional AI system. You use rule-based. You do hand-designed programs, just like we do every other programming. We do hand-designed rules, and then we generate that program. And then it shifted to classic machine learning by a big influence from statistic and information theorem. And then it shifted to the regime called representation learning, and recently it's kind of dominated by deep learning. Rule-based, classic machine learning, representation learning, and deep learning. Question about this?
What's the difference between classic machine learning and representation learning?
Oh, here? Okay. So here, mostly we focus still there before 2010, I think. A lot of practitioner machine learning scientists still spend most of the time design features, design domain important features for priors. And here is through the representation learning when it comes in, we do a lot of, so here it's more like an embedding-based approach or even PCA, CCA, it all belongs to this category. Trying to learn the features by making use of the data. So so not very, but this is more idea-wise, it's a revolutionary, it's very revolutionary. So to have that representation learning idea being proposed, and then, but I agree, there's a big overlap with the representation learning and deep learning. But representation learning, it's more like a superset of deep learning. So of course, there's also this dominating reinforcement learning with the AlphaGo, and there's an agent, and there's an environment and agent idea. It's an interactive formulation. There's also observe, reward, actions. So the action is more like a decision from the F function, and so I'm not going to cover this in this course. The reason is this is huge. The topic here is huge. Just roughly covered by one class. So we're going to cover this when we review the state-of-art deep learning advances, but I'm not going to cover using like more there's no homework. In the end, there's no homework, there's no assignments, there are no quizzes to test reinforcement learning content we're going to cover. It will be pretty short. And so reinforcement learning is actually a very long-term research. It's not just recently get invented. It has a long history inside machine learning. It just recently, by the AlphaGo and deep reinforcement learning, people got reunited. It's just this interest got magnified. But it's a very old topic in machine learning, just to let you know. So when do you use machine learning? When you want to extract knowledge from data, the amount of knowledge available is just simply too large for human labelers to explicitly encode those. So this is the classic case. The second case is we're learning tasks just too difficult to formalize, just to formalize. And it's good, it's a very good, can be nicely formulated through examples. So for example, is face recognition. So to human face recognition, it's very hard to describe by rules, right? So the human face should be whatever. Think about the rules. How do you use rules to figure out how to describe a human face? But it is extremely easy when you have a library of human face examples. And this type of task, really good. They're good. It's hard to describe by rules, but it's easy to describe by examples. So that's why this is a very first few solved tasks through machine learning. And then the other is you want to create software involves with time. Just there are more data, there are shifted distributions, and the rules you just generated, you generated maybe in the 80s, it's just not applicable to the 90s or to current. And those situations you want to create software can be adaptively revised by this automated algorithm. So this is the situation you really want. You really want to have machine learning to be part of the program generator. So in the end, machine learning is to generate programs automatically. Okay. Questions? So one more. So there's also this scalability angles. So there's, I think like 5 years before the deep learning hype, is the big data hype. So in the end, big data is more like, it's a task formulation, right? So when people normally talk about big data, what they meant is about large scale of samples or large number of features. So when you have this many samples, and the way to generate program really kind of changes. So when you have thousands of samples, the type of method you should use is different from when you have trillions of samples. Because when you have trillions of samples, just to feed over that trillions of samples to your program is a challenge. Here, computational challenge is the most critical consideration when you design how to generate your machine learning program. And it's really different mindset when you handle like thousands of samples versus when you handle million samples or billions of samples or trillions of samples. Different skills or different tricks are applicable in the different situations. So keep this in mind. So in fact, in the modern like Facebook, a lot of those big IT giants, what they're using now mostly, so even though we're going to talk about a lot of complicated deep learning models or really complicated kernel machines, but in those situations, the mostly used are linear models. And which is the first few models we're going to cover, and there's a reason for it. And it's about computational cost, how to cover, even how to storage, to put all those data, so you get all those data into your memory, and then trying to do the training is hard. All right, so we're going to cover a little bit about this, and this is one of the things I really like. It's the algorithmic perspective of the different method. So what's the training cost? What's the memory cost when you train a model? So that's why I require students to be able to derive asymptotic form of your whatever we cover, and I think that's a total legitimate requirement for computer science graduate student. So if you are not able to, I recommend you to maybe, so either go over the basic algorithm materials or doing, I think that should be enough. The undergrad level algorithm class should be good enough for that purpose. But the majority of this course is going to cover, so when you have no y, complicated y, or complicated x, or related to X or tractor X, how do you model your pipeline? So that's our focus of the course. So in total, there will be 6 major sections of this, what we're going to cover. So we start from regression and classification of supervised models, and we're going to do the interleaved learning theorems to be in each one of the first 3 sections. So this follows the majority of other machine learning courses, and there's a reason why we do so. The reason is the regression model is the fundamental. It can provide the easiest modules from that 5-module representation. It always it's the easiest to explain. Its loss function is easy to derive. Its representation is easier to write it out, and also its model parameters are also pretty simple. So that's why we start from the regression models. And the variation of regression models can be very easily adapted to the classification cases. So this is the fundamental. So even though the majority of the method you're going to use in your future jobs or your research will be classification or maybe unsupervised models, but this is the elementary modules. So that's why we start from there. And after you have a very solid understanding of what we covered here, it's really just an adaptation to the classification of unsupervised model or reinforcement learning. So reinforcement learning, in the end, there are supervised version of reinforcement learning, unsupervised versions, or maybe semi-supervised versions, and all those relies on the fundamentals. So that's why, please, don't think this like a vintage topics and why do we even cover, and it sounds like not useful, but if you understand this very deeply, it's just very easy for you just to understand those complicated algorithms in this more state-of-the-art setting. So in the classification section, I'm going to cover deep learning, like 2 lessons, just 2 lessons. There will be 1 homework about deep learning, but that's it. Yeah, no more. Yeah. Question about this? You guys are very quiet, but that's okay. So regression, it's about why it's continuous. Classification is about condition why it's discrete. Unsupervised, there's no why. Learning theorem is about properties of F. Graphical models, it's about interaction among feature variables. You can also consider output variable is one of the feature variable. I should revise this. So reinforcement learning, it's about actually your distribution x, y is shifted with the actions. Again, so the mental representation, so you can tell I'm using the task to organize the sections. The task is that y. So in the end, the differences is y defines the task. The differences of the f defines the representation. Then there's scoring function, optimization, and model parameters. The model is about the representation. So so there's a lot of things we're going to cover, and in the end, you can don't think about you're going to learn each individual learning method. What the 2 things I want to teach you is, so across different methods, there's what are the tasks we covered across different methods we cover, all those NumPy 1 line or maybe scikit-learn 1 line of code, you use those methods, underline those algorithms. What are the things shared? Are they linear, non-linear, tree, multi-layer, probability-based, or Gaussian-based, local function-based, or kernel-based, or smoothness regularization-based, or partition-based? So that's the most important we want to learn. It's not specific method. It's this, and the differences among those, each module, and also can you do cross mismatch? So in the end, new method is really just cross mismatch. I can pair nonlinear method with some kind of maybe goodness of interclass similarity loss function to create a new unsupervised method. And that's the most important. To understand the differences and the similarities when they're in the same category is the most fundamental aim of this course. Questions? Good. Yeah, so before I move on to talk about, okay, more concretely, how do you represent the data? So I want to ask a question everyone can just give me an answer. Why do you take this course? Why? What's the reason behind? Every one of you should be able to answer. Maybe people like in that corner. Here?
Yeah, because like machine learning is trending and everyone's doing it and like guarantees a like good job, stuff like that.
Good question. Machine learning is trending, right? And it may guarantee good jobs. Okay? Yeah, so I think that's a good answer. So there are different levels, right, and to understand a topic. So I think the current machine learning reaches the phase to be getting mature. When the field gets mature, it normally gets harder to do research, but gets easier to do applied type of work. And the reason why it's getting kind of a little mature, it's really those great software package libraries. And it kind of removed that obstacles used to be really hard. It used to be very hard to be able to code all those algorithms correctly. But now you just do one line of library use. Good question and a good answer. What other reasons to take machine learning course? Are there some flip side of this? So maybe let me ask a more relevant question. So is your main reason to take the course to use machine learning but not to design machine learning? If that's the answer, you raise your hand. There's no shame about this. Oh, sure. So they're about a quarter. Okay, so for the rest of 3/4, you are aiming for design machine learning, right? Why? What part of machine learning, why do you want to design machine learning? Can anyone give me a question? I'll give me an answer, good answer. Do you have an answer? Sure, yeah, you can. You're the one most close to me.
So I'm using reinforcement learning for part of my research, my PhD research.
Oh, okay.
So as part of my research, I need to reduce the size of the space designed to make it more appropriate for the kind of work that I'm doing. It's kind of dynamic power management. So I need to learn more about the methods that we try to do that. So it's part of my research.
Great, yeah. This makes me feel a lot better because initially I thought, okay, everyone wants to be a tool user or a tool. So there's no shame about tool user, just to clarify. And I like the idea of you want to be a tool builder because this is the purpose of the class. And also for those who want to be the tool user, but in this class, and I think you want to be a good tool user, right? Yes. And just to share you, because I worked in the industry for 5 years before, so normally when for the entry jobs, just using library is fine. It's totally fine. But as years goes by, maybe you go to more management or more architecture positions, you really need to understand fundamentals. And I hope by the end of the whole course, you can understand the fundamentals very solidly and use the libraries correctly, because even though the current library already wrap up all the details, you don't understand too much of the details, but when you go to more advanced positions, and the current library will not be enough. And you need to be maybe even communicate with people who needs to build the library, just to be to revise the library, and you need to understand the details to provide support or maybe to provide feedbacks. Yeah. So in the end, so we want to understand more deeply, but not just, of course, using one line of library use is fine, but our homeworks mostly you can't use those library calls. Just to summarize, most of the homeworks, please do not use those library calls. And I want you to implement from scratch. The simplest is the k-nearest neighbor method we're going to cover later. It's almost the simplest learning method ever. But it's extremely difficult to implement it well. And that really relies on your understanding of scalability, algorithmic design. You can just submit a very basic version, that's totally fine. But to submit an advanced version needs fundamental understanding of KD tree, data structure, and plus good coding. Yeah, so just to summarize. So we have two very wide spectrum of homework grading. So as long as you submit it correctly, we give you a full grade. But that itself also covers a big spectrum. They're really good code. They're also really bad code, but functional. So I want you to be, as grad students, hopefully you can urge yourself to write good, scalable, and nice code. Yeah. So, and that experience hopefully to help you to think about a lot of algorithmic flavor inside machine learning. And that's more like a summary. Okay, so all right, let's come back to what we want to cover is, so how do you represent X? And we normally represent X just by a matrix form. So the matrix form inside what I meant, so each column is a feature, in this case X1 feature, X2 feature, until XP feature. We normally see they're totally P features. And the last column is the target variable. There are many different terminologies saying the same thing. So when people mean like data, points, samples, instances, or records, they're all the same thing, means the row, a row in this matrix. When they say features, it means the column. In this case, X1, X2, or X2, or X3. And the last column is not feature, it's the target, or is the outcome, is a response, or we call it labels, dependent variable, or target variable. Sometimes it's called, so they're all the same terminology, mean the same thing. Last column, other columns, its features, and rows are samples or instances. What we want to get is to F from the X space into the Y space. So, yeah, so just to normalize the, let's have a normalization of terminologies for now. So sometimes I see instances, sometimes I see samples, they're the same thing. So there are many different type of columns. So especially the last column is important. The last column y defines the task. If the y is a continuous numerical value and we're performing a task called a regression. And if the last column is discrete, it's a symbol, it's from a set of possible values, that normally we formulate our task as a classification task. So again, the properties of the last column defines the task. Real number, regression, discrete, symbols, classification. And supervised classification, again, two phases. What you have is in the training phase, you're given this matrix with the last column, it's already labeled with the good values there. You're trying to feed into a computer, you learn the add function, and the training needs input-output pair. That's what we meant. In the testing phase, is the test data. So the test data, the last column is masked. You do not feed the y in of the test data. You only feed the x, and then by applying the add function, the one you just learned, you get predicted f. And yeah, so this is the training phase and testing phase. So supervised regression is the symbol output, and supervised classification is the numerical output. And how do you know it's predicted well? Like we already mentioned, you have one evaluation module. So by applying the f, and you've got predicted f, predicted a, b, b, a, and you compare this predicted column versus this. Actually, because you masked, right? It has the values already. You really just compare these two column vectors by getting the loss or the errors. This is how you evaluate. If you think about, so I'm feeding a matrix in, and I get f, and I'm applying the f on a matrix got masked column, and then I have an evaluation module. I compare this original y vector versus the predicted y vector. That's the evaluation module. So each one of this is actually how you're going to implement through coding, right? That's exactly the different functions you're going to implement. Evaluation, testing, training. Questions? Almost the first homework. Yeah.
What is the improvement?
I'm sorry?
The improvement.
I cannot hear you.
So you said the whole procedure that's part for the improvement of the model.
Improvement part. Oh, good question. So you mean how to learn f by minimizing the error function?
Some signal.
Yeah, so that's next. Yeah. So this really hidden here. It's hidden here in the learn. So how do you learn, right? So yeah, so again, so this is how you're going to implement the first homework. And this is the data looks like. Your training data is x1 to xn. Your testing data is xn plus 1 to n plus m. And I hope you are very familiar with the notations here, because we're going to reuse this notation again, across the whole course. First, let me ask you, when we see vectors, we normally mean the major representation of a vector is a column vector. So what's the size of a column vector, assuming we have p features? We use a column vector to represent a data example. What's the size? It's a vector, and it's a column vector.
P cross N.
Yes, it's p times 1. very important. This is I'm trying to emphasize this again and again because just to match the size can help you understand all those look very complicated equations. So we normally represent a vector. Sorry for people there. I think I can write here. Yeah, it's actually right here. So do you understand this? So there's x1 transposition. This matrix is n times p. N means there are a total of n samples. Total of n samples, you have x and y pair, which the y is here. This y is n times 1 vector. It includes the first y, the y of the first sample, the y of the second sample, until the y of the nth sample. I just put them together into a vector. And it's a column vector. It's n times 1. And the training matrix is n times p. So this is actually representing the first row of the matrix. And this is, so let me get x1 out. So when we write vectors, when I handwrite it, I normally have a bar on top just to represent it's a vector. xi is the ith sample. It's a size p times 1 vector. Because we normally just represent samples as column vectors. That's just a convention. So now, do you understand why there's a transposition here? So this is an n times p matrix, right? The first row is what? If you just think about the first row, it's a vector of 1 times p. It's actually a row representation. But my convention to represent a vector is column, so that's why I have to put a transposition there. It sounds very dry, but you have to understand, otherwise all this later, when I convert into x and w, it's very difficult to jump into details on why this is a good formulation. So there's a reason this is a good formulation I'm going to cover in the next class, but just keep this in mind. Yeah, so more like visually memorize it. And this is the test data. So we have m times p, which is their total m samples. Each one of those is a p-dimensional vector, and their m times 1 samples, actually there are m samples in the test data. So when you do homework 1, what you truly operate on is these two matrices. Of course you can do for loop. You actually totally can do for loop. But I'm going to explain why this is a better representation compared to the for loop representation. All right, so notation, so x sub j, the different columns, what is just big capital letter but not bolded, it normally means random variables. Random variables are represented by capital letter but not bolded. When it's bold, it normally represents a matrix. And yeah, so this is the matrix. We bold capital, and P, we normally use P to represent number of input features. We use N to represent the number of instances in our training data. And the vectors are assumed to be column vectors. Column vectors is something times 1. Its size, in our case, is p times 1. And the discrete type of inputs input will be handled with a special representation called dummy variables. It will be covered in one of the homework. So if you do not understand last item, it's okay. When you do the homework 3, you're going to understand why I'm writing as this. For the output variables, we normally, if it's quantitative, like a real number, I use capital Y. If it's discrete, I use capital C. And just to kind of clarify, make it easier to distinguish with the real case versus the categorical case. And observed variables are written in the lower case. So it's not observed variable, it's observed samples. I should replace it. So for example, this one, so when the variable is observed, it's used the lower representation, lowercase letter. If this is a scalar, it's just not bold. If it is a vector, it will be bold, or I add a bar on top to represent that's a vector. So it still sounds, so try to memorize this, and this is a consistent notation we're going to use, and I think this kind of follows whatever you learned in your previous calculus or probability class. So a few sample slides I want to show is, I want to do derivation. So this is the regression loss formulation, and I always do. I found this practice very important to let students to pass that the fear of doing this type of derivation. This is actually pretty simple. It's a very extremely simple derivation for the regression case because it's quadratic loss formulation. And as long as you finish the calculus, basic calculus, you should be able to understand it. The reason why it looks hard is just because this is a matrix vector form. That's the reason why it looks difficult, but the whole thing is a decomposition. It's just some kind of for loop, cover multiple points. It's a more concise way to represent cover multiple points. That's it. And in terms of probability, I'm going to do a few maximal likelihood-based estimation, and I hope you learned about Bernoulli in your probability class, or binomial and multinomial, and you should be able, because this is one of the minimum tests you did during last week. So I have just a few minutes, and I'm going to do quickly just going over about machine learning histories. So again, like I emphasized many times, machine learning is just a program, and the properties it's really a subset of software programs, and the difference is just how do you create it. The creating process is a little bit different from the traditional software engineering. Use data to create programs. And also this program has, because of the data-driven program generation, it has some kind of special properties because it's mostly in a mathematical functional form. Not like the traditional software you use for case, all those, whatever you learn in your programming class. So here it's a specialized set of primitives, right? If you think about it, just the primitives are different from what we learned in our programming class. And in the 50s, I mean, it's this checker player starts this. It uses the past history of checker playing to learn a good checker player. So that's how the Samuel started this whole data-driven program generation. And then later, there's the neural networks, or the current deep learning. It was invented in the 1960s. It's not invented now. It was invented many, many years before. And at that time, there's already have the multi-layer perceptron. And then in the 70s, we have the decision trees. In the 80s, we have advanced decision trees, and also in the 90s. So 90s is a very glorious time of machine learning. Is you have ensemble like boosting. Boosting was invented back then in the 90s, and also BaseNet. Reinforcement learning was invented by then. And also text learning becomes a dominating application in benchmarking machine learning, actually from the 90s. A lot of things we're doing now is not new at all. And then in the 2000s, and then in the beginning of 2000, there's for vector machines very big advance. And questions? Do you have a question about history? Okay. Then we have transfer learning, collective structure output prediction, or a lot of those kind of email, spam email classification, and application of machine learning or personalization in retrieval, in robotics, in vision, all happened dominantly in the early of 2000s. And at the same time, the machine learning starts to be applied beyond the AI tasks. So in the 2010, so because of this ImageNet competition, the deep learning starts to dominate. Really, it's really an industrial-wide revolution. The reason is it pushes the benchmark result to be 10% better than the previous method. So this field has something, so people care about your competition result in those really large-scale benchmark competition. So it has to be an empirical advancement. It's not just theorem. There should be a very solid, significant advancement. That means the great, true advance of the whole field. So there, you know a lot of terminology here, like DeepMind, Google Brain, Watson, like Google Search, like Google AI, and Facebook Fair, Uber, and OpenAI. There's a lot of things happening now, and I already covered this. So I already covered this too. So it's also related to a lot of other things like psychology, numerical observation, probability, or data mining. So especially deep learning got a lot of this start idea about how brain works. So you can, if you read the deep learning papers, a lot of those terminology very similar to cognitive science, memory network, long, short memory. If you ever read those books, like Think Fast and Slow, it's like long-term memory, short-term memory. We're going to know a lot of those terminologies was borrowed from psychology. So many deep learning methods borrowed the terminology from psychology or cognitive science. There's a reason it's just the founding fathers of deep learning. A lot of those got inspired from ideas from cognitive science or psychology. So again, so now like this hype of AI. So what's the goal of AI? So this, like some people summarize, like AI should think like a human, should think rationally, should act like a human, should act rationally. So if you, this actually create a lot of the current ethics, the discussion about AI ethics. So what do you mean a good AI? So it's very hard to define. So it's kind of related to the question I tried to summarize. So when you have this huge amount of data, so everyone claiming, okay, I want to make real world impacts. But what do you mean real world impacts? Do you mean use computer to replace our employees? Do you mean, like, what do you mean? It's very hard to have a shared definition of real-world impacts, or what is a good AI. So there's a lot of research in social science, in psychology, to talk about or think about this. In politics, actually, a lot of policymakers also think about trying to figure out, because this has so fundamental influence for the whole society. How do we treat this coming AI, intelligent machines or robots, to be part of the workforce? How do you define that's good behavior, that's bad behavior? Not for human, actually for a computer. So it's very controversial. And so this is really just basics. So what do we mean intelligent AI? To be able to perceive the world, understand the world, react to the world. Oh, I need to finish. So milestone I already covered. So the most important is 2012, that 2012 competition from the ImageNet competition. And it's just dominantly better. It's actually it's 2012. It's 85% performance. The previous year is 75. It's like 10% better. It's dominatingly better. But there's a reason why. Neural was invented in the 60s, right? Why now? Why in the 2010? So in the end, there's this huge amount of data collected and also storage. So easy access. And the other thing is the GPU. So the deep neural network is so powerful, it's so complicated. So the old machine just can't fully get this power fully used. And the GPU machines are a fundamental pushing factor to make the current deep learning to be feasible. So it's really a combination of data, computer resources, plus a powerful method to make the combination a powerful tool. And I think this is really the essence of what machine learning really is. You think about computational power and data availability, and then the algorithm. The three combination is to make a good method. And so for the rest of the slides, please just read it, because I try to cover what are homework. So you can because you're going to do the homework, you can understand why do I pick those homeworks. And that's all for